Thank you everyone for coming. Thank you for finding the strength to come to my final talk. I understand not only talks make a good conference, but the activities afterward, and I'm standing between you and those activities. But hopefully today I will tell you about an interesting piece of a technology which exists and is rather like rare used, which is called USB IP, and we will talk about how to exploit it in Linux. Okay, first of all, who am I? I work at Cloudflare. Who heard about Cloudflare? Okay, so yeah, I'm working platform operations currently. My main interests are security and crypto. I also enjoy low-level stuff, so I usually work in Linux kernels, low-level C code, BIOSes, firmware, and other interesting, nasty things. But I'm not like a professional infosec person, so I'm not a pen tester. I'm more a builder than a breaker. But you may ask me why I'm standing here and presenting a vulnerability, because when I use some system, I'll try to analyze it and see if it's, say, implemented, say, which is not what happened with USB IP. Okay, so what are we going to talk about today? First of all, I will introduce you to the USB IP framework. We will see how it's implemented in Linux. I will briefly show you how you can share a USB device over IP network. Then we will jump to vulnerable USB IP code and discuss potential exploit impact. And finally, I will try to give you some advices that if you want to use this technology, what should you do? Okay, but first, this is a vulnerability, so are you vulnerable? Okay, how many of you have heard about USB IP before? Wow, one, okay. And how many of you all have used it? No one, okay. And how many of you have patched your Linux system from last year? Oh, okay, that's good. So the rule of thumb is the way how it's implemented. So if you have never heard about it and you're sure you're not using it, you're safe. Well, if you're using it but have patched your system from last year, you're probably reasonably safe. And if you haven't patched your Linux system from last year, so you're screwed anyway, so I can't help you. There's much more than that there. Okay, so what is USB IP? So it does exactly what it sounds it should do. So it's a way to share a USB device over a network. The interesting part, it's implemented in a device driver agnostic way. That is, it's not designed for a specific type of a device. It works on a lower level USB protocol layer and allows sharing almost any USB device out there. So it does that by just forwarding URBs over TCP connection. So URB stands for USB request block, which is a low-level data structure or a packet in the USB protocol. And basically it's implemented for Linux and Windows, probably Mac, I don't know. So it can be used in different systems. This is the diagram which shows the high-level architecture of the USB IP framework. It's taken directly from the USB IP project website. Here the link is down. Sorry, no HTTPS because it's an old project. Yeah. So and to move further, first of all, we have to understand the terminology in this architecture. So this is a typical client-server architecture. And the roles are server in USB IP terminology is a side which shares USB devices. That is, this is a side where you plug in a real device and you're supposed to share it over the network. And the USB IP client is the side which imports USB devices from the network. That is, it doesn't have any physical devices plugged in, but when it's imports a device, local system shows you as if you're locally plugged in your imported device. Is that clear? Or? Yeah, so let's now take a brief look how this architecture maps to Linux components. So basically, we have user space components and kernel space components. So they're showed in green. So in user space on server side, you have a daemon called USB IPD, and then you have two kernel modules, which are USB IP host and USB IP core. On the client side, you have USB IP client utility in user space, and you have again USB IP core, which is the same module as server. It's like a shared library in kernel. I don't know, for some reason they decided to put it in a separate kernel module. And you have VHCD, which stands for Virtual Host Controller Driver, so it's a virtual USB host on the client side. So how it works, in high-level overview. So imagine you have a server and you plugged in a USB device. What happens under the hood is the USB device starts communicating with your real server's USB host controller driver. Then host controller driver reports that it enumerates as USB device and reports that it found a new device on the bus. And in modern Linux distribution, we all use udev, which will find an appropriate device driver for this USB device and load it into memory, and then driver will start communicating and controlling the USB device. So, okay, so now imagine you plugged in your device, that's how it will work, and now you want to export this device over IP to the client. So what you do, USB IP daemon sends a command to make this specific device exportable. So under the hood, USB host controller driver disconnects the real device driver and starts forwarding all your URBs, these small USB packets, to the USB IP framework. Yeah, and it stops there for some time. So it means, so the device disappears from the server's operating system, but since we have no client, nothing happens, so it stays in this way. Then at some point, client comes in, and the client wants to import this device, so it sends an import request to the server. What happens under the hood is that server and client establish a TCP connection, and then the server starts forwarding these URB devices to the virtual host controller driver on the client side, and then the virtual host controller driver behaves like a real host controller driver. It reports that it discovered a new device in the system, and udev will load the same device driver on the client system, and that device driver, the client, will now be controlling the device on the USB IP server. So this is how it looks from command line. This is a client perspective. So first of all, to import a USB device from a server, you use USB IP client utility, you issue a list command, and you specify the IP address of the remote server. In this test, I did it like a localhost test, so this is a localhost address, and you get a list of all the devices which are imported from that server. So the needed information here is that ID, which is 1/1, this is like device ID in USB IP terminology. So to import this device, you just run this USB IP client utility with attach command. Again, you specify the IP address of the server and specify the ID device you want to import, and after that, the magic happens and you get this device on your local system. So when I originally researched that, what was interesting for me is that in server side, you have the USB IP daemon, this daemon which runs in the background, like providing the server functionality. But on the client side, when you issue both these commands, the USB IP client utility exits immediately. So if you kind of like compare what I would expect from a framework like this to be implemented similar to a VPN solution. So this is like how typical VPN works. So basically how VPN works, it takes the underlying network packets, encapsulates them in like other packets and forward them the connection. But the architecture is, so both sides of the VPN solution, they have some kind of VPN agent in user space which provides the VPN functionality. And those agents establish a secure tunnel between themselves, and the kernel only provides this low-level function of getting the low-level data structure and sending it to the other side. And I was expecting the same architecture from USB IP, but I noticed that USB IP is a like utility. It exits immediately, and it doesn't have any agent running on the client system. So I even tried to search for this agent, but I have never. I thought like maybe when you launch the USB AP client utility, it like forks in background and runs and keeps the device connected, but there is no such engine. And I was like, what? Then I start digging into the source code. Turns out under the hood, the USB IP is implemented a bit differently. So this is another perspective. So what happens in reality when you ask the server to send you a list of exported devices, the kernel is not involved in any way, so it just the USB AP client utility sends a request to USB AP daemon. The daemon maintains a list of exported devices in memory somewhere and just responds, here are the devices you can import. Then the interesting part happens when you import the device. So again, a USB AP client sends an import request to the server. The server still verifies that this device is being exported, sends the success request, but later there is no user space communication happening on the client and the server. What they do is they just pass the established socket file descriptor directly to the kernel, and then kernel directly establishes this this tunnel. Yeah, so basically there is no agent. The agent is the kernel itself, and yeah, the kernel handles all the communication between the USB IP parts. And I was thinking, wow, this is probably scary. And implementing application level protocol in kernel, I know it's a bad practice, and only one popular operating system does it with HTTP, and it's continuously a source of bugs. So I decided to sanity check the USB IP protocol. So that brings us to the next part, the vulnerability. And to understand the vulnerability, I will briefly describe the USB IP application level protocol. It's pretty easy and straightforward, and it's documented in Linux kernel documentation, and it's not any different than any other network protocol. So that it has a header section and a payload section, and basically, as any other network protocol, this payload has some length, and this length is a field in the header. So what could be easier than that? Okay, so if you look at the kernel code, these are all the extracts. So the receiving a USB IP packet on the client side from the server contains two basic steps. One is parse the header, and the second step is get the rest of the data from the network buffer. So if you take a closer look at the parse header stage, what the code does, it just takes what it receives in the header and initializes struct URB, which is in kernel representation of the URB in Linux kernel. So basically, it's not USB IP specific, it's the structure which is used to interoperate with different USB subsystem in Linux kernel. And the interesting point here, we take this actual length and just analyze and just put it in the data structure. Then if you take a closer look at receive of the rest of the data portion, you'll see that there is a local size variable which is initialized from this actual length, and then the size variable is used to receive the rest of the data from the network buffer. So basically, because of this chain, the size variable here is controlled, comes from the network, and basically can be controlled by an attacker. So technically, if you put some data more than the receiving buffer can hold, you get a buffer overflow. That brings us to the conclusion that it is possible to write arbitrary length data to the URB transfer buffer. So what is this transfer buffer? URB transfer buffer is usually allocated by USB core code or USB device driver, depending on who is from USB subsystem is the receiver of the URB. And technically, because how USB protocol works, USB protocol is always host to device. So uh, even though the data is being received from device to the host, it is still being done by the request from the host. So this buffer is allocated even before the host, or in USB IP terminology, the client sends the request to the data. So the code cannot allocate this buffer after it receives the response. So it cannot allocate large enough buffer to contain any data. So USB protocol has a lot of these assumptions that a specific request will not be bigger than X. And according to the USB IP protocol, the packet with large amount of data is totally valid. So if you want, for example, to use some network analyzer to filter out these bad packets, like a network which scans for network vulnerability, you won't be able to do that because from USB IP perspective, this malformed large packet is totally valid. So, okay, you have like a big amount of, you have a large number of the size portion in the header file, but you have the same number of bytes in the data portion. So it's no in any way invalid, but your network analyzer does not know that probably the receiver side client buffer cannot contain so much data. Okay, so this received a CVE number, 2016-3955. Surprisingly, it received a very high CVSS score. It's almost 10 out of 10. And that's because, for a number of reasons, but probably because this is network exploitable and requires zero authentication to write arbitrary data to the kernel space. And although I'm not a fan of giving nicknames to vulnerabilities, I find that like security researchers find it hard to remember CVE numbers, so I just came up with a name. It's called UBOAT, which stands for USB IP Buffer Overflow Attack. Unfortunately, I'm not a designer, so I don't have a cool logo, but if someone wants to contribute a logo, so please send me an email. Okay. We've seen the code, might be a little bit confusing, but what the conclusion is. The architecture of USB IP, it cannot be exploited easily, thankfully. So what are the requisites? The requisite is that your victim has to actually use USB IP in the first place, because USB IP has been merged into mainline kernel since version 3.17, and it's by default enabled in most major Linux distribution, but the problem is by default it's compiled, the modules are compiled as separate kernel modules, not in-built kernel functionality, and all USB IP tools explicitly load those modules when you start using this technology. So technically, if you don't use USB IP, probably the modules are not loaded, so probably you are safe because you don't have any vulnerable code in your kernel. Victim has to be a client in USB IP terminologies. It's basically the site which imports USB devices, because the code path is different from client and server, and I haven't been able to find the same exploitation path for the server side receiving code. Okay, victim has to import at least one USB device. So as we've seen before, there is a small handshake before the socket file descriptor actually gets into the kernel, so it happens only on successful import of one device. So you, an attacker, have to somehow force the client or exploit an existing USB IP connection. If the client does not import the device, you don't have the socket in the kernel, you can't exploit the vulnerable code. And again, as an attacker, you have to either do MITM to handcraft these big data payload packets, or you have to somehow control USB IP server and make the server send malicious packets to the client. Oh, demo time. Okay. Okay, just a moment, please. So the demo will involve like how you can break the you need a client and a server for the demo, but again, for the demo, I will do it on a single host, like on single virtual machine. So this is like a standard, this is a standard Ubuntu, except it has an unpatched kernel. So it's, let me log in. Is that visible? So for the demo purposes, I imagine that I'm an attacker. I won't do MITM because it's a little bit harder. So I imagine that I'm controlling the USB IP server. So for this specific demo, I wrote my own USB IP server, which mimics the default behavior, but then sends malicious packets. So I will start it. Tell me if I'm missing something. Okay, so the server is running now. First, we can verify that it works. So, sorry, I don't see what I'm typing. So let's first check which devices are exported on the server. Sorry? Okay, let me do like this. I will. Okay. So yeah, we have logging here. We see sending fake device list. So I report to the client that I'm exporting a very dangerous device with hardware pass is fake dangerous and with product and vendor ID of dead beef. And so nothing to worry about. Yeah, so the client, so yeah, as I mentioned, like we want to import this device, but before doing that, we need to explicitly load USB IP kernel modules. So I'll do that now. Password. Okay, success. This USB IP core and the virtual host controller interface. Okay, so now we can import this device. So we will say attach remote and the device ID 1/1. Okay, so it may crash the system or may not. We'll see. Something is wrong, right? Let me check. Sorry. Ah, there is a space here. Okay, one more try. Thank you. Yes. Yeah, and this is what I wanted to mention, that although to import the funny thing is to import a USB device, you should have like super user privileges, but to run a fake USB AP server and crash other clients, you can run it from normal user. Okay, let's try it now. Oh, okay. So here we see server logging that the actual buffer of the receiver is 64 bytes, but we sent him 576 bytes. And does it have? So we see something happened, right? I'm not sure if it's usable now. Let's try. It's still live, but sometimes it fails immediately. Sometimes it fails later. I have found it usually fails when you want to see the mask. Okay. So yeah, we overwritten some weird data and we crashed the server and nothing works anymore. So it should say at some point, yeah, so it says like reboot is needed. Okay, let's go back here. Okay, so what can you do with it? First of all, you can do a denial of service attack, which is seen, but you can try to do better than that. So you can probably do data injection or even try to do code execution. It's worth to note that here we have a standard heap exploit, and due to the random nature of heaps, code execution is rather hard when you have a heap exploit, much harder than when you have like stack memory overflow, because in stack you just override the return address and you're good to go. But in heap exploit it's much harder, but it's still possible. I will not describe the full process. I will just reference to you to this blog post. This blog post exploits another vulnerability, which is also a heap exploit, but it has a detailed step-by-step instruction. What should you do to exploit, to make code execution when you have a heap exploit? It's a bit outdated. It doesn't take into account recent kernel technologies like random address randomization and other security mechanism, but still doable and adaptable to the current state-of-the-art exploit development. I will briefly describe the high-level overview how you manage what's the difference between this exploit and other potential heap exploit out there in the Linux kernel. Turns out the USB AP vulnerability gives an attacker much more possibilities. We'll see in a second why. So when you have a heap exploit, so you have to understand how Linux memory manager works, and this is like the basic stuff. So how it works is that Linux reserves some portion of memory, some addresses, and breaks them into equal pieces, which are called slab caches. So we have like a slab cache of 32, we have slab cache 64, which is a chunks of 64 bytes, and we have slab cache 128, which are equal chunks on 128 bytes. And it doesn't have to be a power of 2. There are slab caches in between. It's just for illustration purposes. And when your code says, like, okay, I need to allocate, let's say, 28 bytes, actually under the hood, the kernel will search for the next available slot in the smallest slab cache available. So in this point, it will select slab cache 32 and just return you the pointer to that piece of memory. So basically you always get a little bit more than you request, but as long as it's not less, so it's fine. So what does it mean to have an exploit where you can override past the boundary buffers? What it means that you can technically write anything into your buffer and all the buffers which happen to be after your buffer, and it's based on your luck or how you approach the exploit development. So what's in that buffer? So probably these other pieces were allocated to other kernel subsystems at some point, and if you're lucky that the adjunctant pieces contain some kernel control structures or address pointers, you can technically override them with your values and change the code execution of some kernel subsystem and do the exploitation. So, but the way how USB AP different is that usually normal kernel exploits are designed in a way they can only exploit a single slab cache. That means somebody has a vulnerable code which can override only slab 32 caches or slab 128 cache. So you have to build your attack based on that assumption. USB IP vulnerability gives you much more flexibility in this, because technically, because you control the USB IP protocol, the USB packets which you send to the client, you can technically emulate any USB device on the client side. And because the kernel has a lot of different USB IP drivers, you don't have to necessarily exploit the first packet you receive. You can just scan the kernel source code and find the yeah, this is what the list says. So you can literally select whichever cache you want to exploit. So you're not bound to the and you can exploit almost any dynamic data structure in the kernel. So what you have to do is you just scan the USB all the USB drivers available in mainline Linux kernel and find the ones which allocate buffers in the slab cache of. Is everything okay? And find devices which allocate buffers in your desired slab cache, the one you want to exploit. Then you not necessarily send the malicious packet at once, but you emulate the full USB protocol and trick the client that you're that specific device of your interest. So the client's UDEV subsystem will probably load the appropriate device driver on the client subsystem, and that device driver will start allocating memory in the slab cache of your desire. And then you do your overflow. So you're not constrained if you want to attack a specific data structure which is allocated only in specific slab cache. You are not constrained by this exploit, so you can adapt your exploit to target a specific data structure. Okay, still want to use USB IP? Yeah, if you do want to use, here are some tips. First of all, reconsider. So what are the advantages? So today's USB devices are rather cheap if you just buy another one, if your target is just share a USB device. Second one, patch your system, patch often. It does not relate only to this vulnerabilities. Vulnerabilities are discovered every day, bad and worse, so you have to stay on top of security patches. Protect your traffic. The funny thing is, the whole project provides, even if you don't have the vulnerability in USB IP subsystem, technically you still have very dangerous framework, because if I'm an attacker and I am able to hijack an even valid USB IP connection, I can emulate any USB device on the client subsystem. And luckily today we all heard, we all listened to the talk this morning about the dangerous USB devices and how much harm they can do. But the main constraint there was that you have to have physical access to the machine you want to exploit. But this framework just removes that constraint. So you can now do the same USB attacks like for physical devices, but over a network without zero authentication. And original USB IP project, maybe because it's old, does not even recommend you in any way to somehow protect your traffic, and it does not have any, the user space tools do not have any inbuilt capabilities of securing your traffic. So definitely use TLS or IPsec, and even in intranet, because people say, oh, okay, my internal network is inaccessible and it's secure, but you have tons of IoT devices, and we know how good IoT devices are at security. So, and lastly, ensure your USB IP server is trustworthy and with proper ACL. So if an attacker cannot hijack the connection between you and you as a USB IP client and the server, so the attacker would definitely try to hijack the server itself and try to make it send you malicious payload. So locking down USB IP server is also very important. Here are some resources. The first link is linked to my blog post describing this vulnerability in more details. So it has exact references to Linux source code, where the patch is. If you want to follow, please do. The second one is a source code of my malicious demo server. Originally, I wrote it in C. It was very ugly, so I decided to rewrite it in Go, and now it's very easy to understand, and you can adapt it to your needs. The third one is a link to the CV database, which describes the vulnerability, and it actually has a breakdown why the vulnerability received so high severity score. Sorry. So the third link just describes the vulnerability, and the fourth link describes the breakdown why the vulnerability received so high CVSS score. So basically, as I will repeat it, because it's network exploitable and requires zero authentication, and there is no like traffic encryption. That's it. Thank you.